So now we have Bridging the Gap with Data Science from Florian Wilhelm, from Innovex. Applause.
Hi, welcome everybody to my talk, Bridging the Gap from Data Science to Production. Before I start, a few words about myself. I'm a data scientist at Innovex, and being a mathematician, I really like mathematical modeling, so solving riddles and trying to express some real-world dynamics somehow with formulas. I've done some projects in recommendation systems, which is also a topic that I really like. Of course, I'm a big proponent of data science in production. That's also one of the reasons I'm giving this talk. So I really think you have to show the value of your data science by showing it to your customers and not just doing one proof of concept after the other. And I'm also a big fan of the Python data stack. So whenever it comes to Python, I'm surely a little bit biased. Then, a few words about Innovex, the company I work for, and who give me this nice opportunity to speak at cool conferences like this one. So Innovex is an IT project house. We are doing agile development and management, developing apps, web, mobile. We also do coaching. We also have a team for operations and IT, and of course, big data and data science where I work in. And we have offices basically all over Germany, also one in Hamburg. So much about a little marketing for us and the actual topics. So I've done quite many projects in data science and actually recognized that quite often you do one cool proof of concept, one prototype after another, but it never really moves into production, and people are struggling with this. And at Innovex we also sat together, and it's not actually the exception, it happens quite often that teams struggle with this, and we thought, okay, let's bring together all the experience we have and talk about the challenges and how you can overcome them, what you have to think about when you want to move to production, and this is a kind of assembly of this. So how many of you are actually data scientists? Maybe just raise your hand that I can get an impression. Okay, and how many have you worked in some data scientist related project, maybe in another role? Okay, and have you had the same experience? Was it easy to go in production? For whom was it really easy to go in production? Okay, so for no one. So I guess it's a relevant talk. So we first start by looking at the actual use case. So try to do some kind of taxonomy, how you can kind of categorize the use case and already get information about how easy it is or will be to move into production. So on a really high level, you can just think of your data product as having only three components, like data, then you have your model that does some transformations, predictions, or some kind of decisions, and in the end you have the results. But already with this really high level perspective, you can make there's already different categories in a way, so different variants. For instance, are you accessing your data with the help of some database or some distributed file system, or is this data use case you're working on relying on stream data, maybe by Kafka? So this is something where you can write at the start when you are doing some proof of concept and someone just gave you some CSV file on a USB stick, ask yourself, but what will happen later on? How would I get this data later on when you want to move into production? And of course, depending on your use case, also the frequency and recency requirements. So meaning, is that what you do? Is it rather batch related? Maybe you're doing some demand forecasts for the next weeks, and it's okay to do this, to bring updates once a day. Or maybe you're doing some recommender where you really know, okay, it's real time. So people on your website and you have to give recommendations in under 200 milliseconds, for instance? Or is it something that you more or less do stream-based? Then the model, and whenever I talk in this talk about the model, I'm actually meaning not only the machine learning algorithms, so not only some random forest or some artificial neural network. I'm also talking about all the pre-processing you do given your raw data, and also the feature engineering, of course. And so that means cleansing, imputation, scaling, construction of derived features like exponential moving averages. All this is part of your model. And the more you have of this pre-processing, the more complicated it also gets to bring this in production, of course, because it's not enough to bring the machine learning part over. You have to bring this whole pipeline over into production. And yeah, and also if your model has some kind of state and so on, you have to think about this early on. Then later on, what do you do with the results? Is it also that you just store it in some database, in some SQL-like database, or in some file system, or again, you just post it as a new topic in Kafka, or maybe like, again, in the recommender case, you have to provide some REST API and have to provide this on demand. And there again, you have these requirements where you have to think early on, because this will decide on your architecture and how you set all this up. So again, now our challenge is that we want to deploy this part, so the model part, and this means that we have to define interfaces with other teams, or something where you can rely on, that you say, okay, this is the structure of the raw data, how we get it, and this is how we provide the results. And it's important to decide early on with the other teams how you do this. So what we came up with at Innovex is that we said, okay, we want to early on, before we actually program something or so, want to discuss with the customer like the requirements of the use case, that we use a table similar to this. So this is a little reduced version, that we talk about, okay, how do you want whatever we gonna do, like predictions or decisions or whatever, do we deliver them as a web service, stream or database? And then also the kind of problem class, because nothing is worse, for instance, that you do some fancy neural networks and later on someone tells you, well, we need some explainability. And also the volume and velocity. So here again, are we talking about 100 gigabyte of new data weekly, or just a gigabyte, or are we talking about 10,000 events per second? So this is something you can actually clarify before you even start to code. Also the inference, is it batch-based, near real-time stream, just what I said. And the last column is actually an important one. So what kind of technical site conditions you're dealing with. So maybe a customer says, okay, we only have a Java stack and everything needs to be in Java, or we allow Python also if it's going to be on-premise or AWS cloud. So it's just important to understand that there's like no one-size-fits-all solution, and that you should early on write down those requirements and think about them. So status requirements, also identify and check the data sources. So not just this, what I said before, this USB stick or some large file that was somehow shared with you. Then define these interfaces, and it's also a good thing to start testing the whole data flow early on. So just make some dummy model and try to fetch the new data, the recent data, and try to write some dummy predictions into the final store. By this you can then easily find out if someone is complaining or if it's technically possible, or maybe some ports are not open and so on. So this is really a high-level perspective from the use case. Another important thing actually is quality assurance. So how many of you know this CRISP DM? So the cross-industry standard process for data mining. So this is something really old. It's from the last millennium, actually, I think 1998 or so, by IBM. And they define this iterative process that when you do something, you start with a business understanding, data preparation, and so on, and you deploy your model, but then it goes on and on and on. And if you build any kind of data product, it's actually quite the same. So it's not a one-shot thing. You're going to iterate and iterate. If you iterate, it of course is of paramount importance that you have the quality. So that means that you, for instance, you're going to read your code much more often than you actually write your code, which means that one should adhere to clean coding standards. And so what I've seen quite often is in some data science projects that, especially data scientists, so they think, okay, well, I know statistics, I know machine learning, but I don't care that much about programming. And it's important to get this mindset that also the programming is an important aspect of building a model, that one uses design patterns, especially the clean code developer standards. These are things you can apply also with any kind of language, so be it Python, R, or whatever. And if you're working in a team, tell them about clean code. So some people just don't know, some are just ignorant. I knew one guy who said, well, I'm a data scientist, I know statistics, I would not, I mean, on the other hand, some software engineer, I would not expect them to know statistics, so why should I know how to program decently? So they're like, whoa. So it's an important mindset to actually, yeah, to make clean code. Another thing is, I mean, also in this conference, there was a lot of talk about continuous integration, continuous delivery. Start early on, versioning your stuff, make decent packages, manage your artifacts. Of course, unit tests is an important thing. Automate as much as possible and embrace some kind of processes. And the standard tool that everyone uses is actually Jenkins, and it was also used in most of the projects I worked with. Another important aspect is monitoring when it comes to production. So monitoring is important because if you don't have it, it's like flying a plane, an airplane, blindfolded. So you have to track your KPIs, like in a recommender case, for instance, the click-through rate or the conversions. Also, like some hardware things, like number of requests, what timeout delays, maybe it's not scaling enough or whatever, and keep track of the total number of prediction. Maybe after some updates, the model is doing something wrong, or there's wrong new input data, and you're missing something. So it's just important to track everything. And if you read the Google Site Reliability Engineering Guide, so they have this, I overtook this nice pyramid, and they say for any kind of product, the most fundamental thing actually is monitoring. And yeah, this is actually, I totally agree with this. When it comes to monitoring and data products, you can also start thinking about special monitoring regarding the output of your model. For instance, in this case, let's say you have some classification between cats and dogs, and cats are 0 and dogs are 1. And if you make a histogram over the probability output of your model, you could easily see that in the A case, you have a working model, so it's discriminating between those two classes. And in B, you have a rather confused model. So if you see this after you've deployed a new version, after half an hour, you can directly roll back to the old version and start looking for the actual mistake or error you have. This monitor is also important if you want to do any kind of A/B testing. And I mean, that's, this experimental mindset is important to see if you're actually improving. Because if you do offline evaluation only, you of course are not sure if this better metrics in your offline evaluation will also show online. That means you have to compare with the current baseline and compare with the online metrics and KPIs. You can also use it, for instance, to find some final hyperparameter online. And this means, again, you have to version your model to do this. You have to be able to run it at the same time and roll back. And another important thing is you have to track the results of your model actually to the point where they are used. So, for instance, if you show a recommendation, you have to be sure that this is the recommendation you're showing to group A coming from the model A. So you have to keep track what happens with your results. And actually quite cool tool we were using once is TensorFlow serving that helps you to easily manage different models and load them and roll them out and so on. So another facet is are more like organizational or cultural differences. And this is something that is completely not new. So if you look back at like the relationship between developers and operations, you had it quite often that developers said, well, we are responsible for the code, for testing, releases, version control, and so on, continuous integration, and we have done that. We make this nice little release and throw it over the wall of confusion. And then operation had to care about how do we package this, what's in there, how to deploy it, to do the configuration and monitor this. And this already, I mean, everyone knows DevOps, and we need something like this also for data science, because there in this culture of thinking this is not my problem is especially dangerous. So this not my job thinking hurts, and you should always think like, yeah, we made a good or great data product, and not I made a great model. That's my only job, making some cool model that shows some nice root mean squared error, for instance. And again, here we can learn as data scientists and as people who want to build a data product from DevOps, that we overcome this wall of confusion and start doing this in larger teams, like from creation, packaging, releasing, configuring, monitoring, and then again planning and so on, this whole iteration as a huger team. And so from my experience, it really is that pure teams of data scientists, actually, they struggle to get anything in production. So it never happened to me that I saw a team of 5 data scientists that actually, brought something in production. They come up with a lot new models really fast, but no one can really use it. So this means in your team, you have to have software engineers or data engineers, and so our rule of thumb is that per a single data scientist, you need at least 2 to 3 engineers or software developers. And it is data engineers are then people who also know to do how to do operations, and it also helps for communication with business that you have a data product manager in this team, and if your use case is somehow related to some end customer, like on a web page, then of course it's also nice to have some UX and user interface person in your team, because this will also quite drastically change the key KPIs and what you monitor if, for instance, some graphic representation changes. A company that actually did a lot around this and that actually propagates like vertical teams that are independent is Spotify. So if you're interested, it's a really cool blog post, and you will later get the slides. And they have this idea of fully autonomous teams that have end-to-end responsibility. Of course, they work with agile methods, and this allows them to deliver much faster and get things directly in production. So another aspect that I saw where people actually struggle a lot is what I call the two-language problem. So it quite often happen to me that if you go to a customer and they're more like, let's say, a little bit more old school industry, but doesn't even have to be so old school, they really like the Java stack or maybe even the Scala or something. So they say, hey, well, it's a strongly typed programming language, it's much better. We need to have something that is robust and handles all the edge cases, and we already have this huge tool chain to deploy those things, and there are certain industrial standards. But if you talk to data scientists, they want to do something really fast, and they often prefer Python or R. They like it more like a dynamic way because it's much easier for them. And their emphasis is much more on fancy methods and results. And they're actually happy if it runs on their machine. And now you can think of, okay, if you have those requirements, there are many ways what you could choose how you do this. And some of them actually are bad, some are better, and I'm just gonna present you some of them. So what you could do, for instance, is that you just say, okay, well, let's go for Java. Okay, here's again, I'm a little bit Python biased. That you just say, okay, the data scientists, they have to learn to program in Java. The good point, the really advantage of this is that this drastically reduces the complexity, of course. If you have all your Java stack, then it helps a lot if everyone is programming in this. On the other hand, you are completely abandoning an ecosystem. So in the case of Python or R, it would be all those nice libraries and packages that allow you to do machine learning and statistics. And you're kind of sacrificing them for reduced complexity in your deployment. This would be the Java case. You could also say, well, why not do Python in production? I mean, this works quite well for batch prediction use cases, but actually I've never done something like really real time with Kafka related in Python, so I don't know there. So maybe in some cases it doesn't scale it well. So it's again dependent on your use cases. But you're on the other hand sacrificing then all the benefits of Java. What you can do with Python, of course, you can always have a nice web server, maybe using Flask, put everything into an isolated container, and if this is possible in your organization, then that's also a way to kind of get around these restrictions. But yeah, and you can use, for instance, certain libraries to tap into the Hadoop ecosystem, like PySpark and PyHive. But again, here it's like you're losing something. So PySpark and PyHive, they're not as advanced as their Java counterparts. So again, you are sacrificing something, and you should be aware that you do this. So another solution how you could overcome the two-language problem, and this is something that I really experienced, is that you say, okay, well, data scientists program in Python and R, and later on we're going to rewrite everything in Java. And as you might have guessed, it's a lot of efforts and slow. It's also really painful in a way. If you later on want to integrate new features, it's so if you do this iteration, and we said there's going to be iterations if your data product is successful in any way, then to implement new features is going to be really hard, because if you start trying things in Python or R, then you later on need to do the conversion again and so on. Also, if you have any kind of bug in production, any error, it will be, of course, always a finger pointing. Who's responsible? The one who wrote the Java code or whatever code? Or is it in the original model some problem? And it makes it it's going to make it extremely complicated. So the only pro that I actually see is that everyone gets what they want, but for me it's a worst case scenario. Another one is that you use different languages, but agree on some in-between formats, like there's PMML and ONNX. So ONNX being the Open Neural Network Exchange format, and meanwhile there's also the NNEF Neural Network Exchange format, and there are many of those. They really work great in theory, but of course they always have a limited set of functionality. So if you agree on them, you can only do what this in-between language supports, and you, as always, never have the guarantee that you use like a PMML tool in Python and export it and read it in Java, that the result is going to really be the same. I mean, the same goes, for instance, for HTML, right? I mean, no two browser going to render the same HTML page in the same way. And of course, for those things, the same might happen. And also think about your pre-processing, about the feature engineering. Because what we said in the first few slides, that the model includes not only the machine learning algorithm, but also all this imputation of missing values, rescaling, and feature engineering. And you have to think that you also need to do this in this intermediate format. And many of them don't support that much of such transformations. Another framework actually is another way of overcoming this two-language problem actually are frameworks. Commonly used are like TensorFlow, for instance, or H2O, or Spark. And many of those have various bindings for different platforms. So for instance, TensorFlow, you can do this computational graph in Python. You can export your model in some kind of binary format, and you can then read it in Java and deploy it on some kind of web service. Again, you have to be careful about if the framework covers everything. We did some projects with H2O, so this is a really, so if you're looking for some framework that you can use with different languages, H2O is quite good. So we had it that we programmed something in R, and then in the end you save your model in some so-called Mojo file, and you can read it in with Java, and it worked quite well. The problem there again was this feature engineering, where we had to kind of work around how we express this in a language independent way. So if you decide on some kind of framework, you have to be aware that you're kind of agreeing on a framework, so you're sacrificing the flexibility for the ease of use. And yeah, another one is Spark. So I really like Spark, but again, Spark is only for batch use cases. So now we have seen different ways to handle this problem, and like three major cases. And I would argue that what you definitely should not do is like reimplementation. So if someone comes up with the idea, yeah, well, just do whatever you want to do in Python and R, and we're going to re-implement it in Java, so that's definitely not a viable solution. Frameworks, so for us, they work quite well in some projects. And if you go for a single language, then definitely choose rather Python, because the machine learning and data science in Java is really hard. Okay, back to our initial one. So what else is there to say about the data science to production? Another important aspect, of course, is the deployment. And as you might have guessed, so this really heavily depends on the approach you've chosen and on the initial use case that we talked about. Still, again, important are software engineering principles, so do all the clean coding and so on. Think about continuous integration, continuous delivery. And one thing I really found fascinating is from an old paper of Scala, and he or they, the authors of the paper, they made a survey, an analysis of technical debt in machine learning. And as it turned out, that the technical debt of the actual machine learning code was quite small. So all the other things, and especially a lot of stuff that is related to deployment, like the monitoring or your serving infrastructure, it had a lot of technical debt in them. And it's for me it was really like a cool thing to see, and it really opened my mind in a way that that there's so much more than just your machine learning code being a data scientist. So because many people just concentrate on this small bit, but actually it's much more operation and data engineering and so on. So again, to the general principle, think about the versioning, the packaging, have your defined processes and do quality management. Another thing is that you should keep your development and production environment as close as possible. In the morning there was a really interesting talk about continuous feedback, and they even proposed to speakers that you should test directly in your product environment, which I found really interesting. And because it really often is the case that people develop under completely different conditions than the conditions that will later be in production. Automation, of course, continuous integration and so on to avoid human errors. And another thing is that it's good to have isolated and controllable environments. So if you program in Python, then to have something like virtual environment or conda environments or even Docker containers, they help a lot. Again, Google also has thought about this, and they made some best practices for machine learning engineers. I've just written down my kind of best of all of those rules, so we're not going to go through all of them. But again here, so the most parts of making a data product are actually engineering problems. And the rule number one is something I really like. This is again this, don't be afraid to launch a product without any machine learning. So come up with maybe something dummy based and just test the whole thing from end to end, have some kind of walking skeleton, and then later on add this like the AI part of it. And also rule 2, again, implement the metrics and so on. So you see, it's actually much more than only the machine learning part. A little blog post we wrote ourselves at Innovex is how easy it actually is to do continuous integration. If you start a project and setting a really simple Jenkins some pipeline up is really easy. So in this case, it's for a Python package, so that you have your Git repository, you build a package, you push into some artifact store. This is also, I don't see that often actually in the real world, that people kind of push their package somewhere where other people can use it and actually do packaging. So instead of just having a bunch of modules laying around, and that you have the unit testing and so on. So if you want to read about it, then I'll also post, again, as I said, the slides later on. For Python package distribution, how many of you actually use Python? That would be interesting to... Okay, a lot. Okay. So, and how many of you know PyScaffold? No one. Okay, good. Then, yeah, check it out. It's just an easy way to set up a Python package. So you basically just install it with pip install and put up my project, and then you have all this nice skeleton of a proper package, including your setup py and your docs and your source folders and so on. You have a Git integration, meaning that if you tag, for instance, a version in Git, this will be directly reflected in the version of your package. You can combine it with things like pre-commit that help you check if you agree to some PEP standards or PEP 8 or whatever, so depending on what you set there and so on, you can do all the declarative programming in setup config, and it follows all the community standards. And you also have a lot of extensions available, actually. So this is already quite the end of the talk. So to wrap everything up, the key learnings actually are that it really depends on your use case, what you want to do, how you bring data science to production, and there's no one-size-fits-all solution. So whenever someone comes to you and tells you, well, I got this special framework and it will do it for you, it's never going to happen. So it really depends. Then think early about quality assurance, and especially also about clean code and so on, and raise the awareness of this in your team. Then have heterogeneous teams and bring in the DevOps culture and the complete team responsibility for the data product, to overcome the two-language problem if you have it. Either go on and agree on some framework, or choose a single language, and embrace processes and automation after all. The most important thing, so if you remember only one thing of this talk, then production is not an afterthought. So think about it early on, and not just start and develop your models and later on some magic is going to happen and it's going to move into production. So think about it early on. With this, I want to close, and as I said, I'm going to post the slides later on Twitter and SlideShare if you're interested. And thanks, and I'm open for some questions. Anyone? Questions?
You mentioned PyScaffold. How does it compare to PyBuilder?
I've actually haven't used, so a lot of people are using Cookie Cutter, and but PyBuilder, I think I haven't actually used it, sorry, but I'll also try it.
Do you have experiences with like using cloud to put in one's production, because several clouds offer services where you just train the model there and also have it like uploaded it somewhere and it will be served automatically, and you don't have to take care so much of the details of running it through a container and all this stuff?
Yeah, it really, so I haven't used cloud resources that much, or more on a lower level, that I really had to install the things on on this virtual machine then myself, or run there the web service. I mean, the thing is, you have to always separate between training and the inference time. And during training, you most of the time, for instance, again, it depends. If you have, for instance, some deep learning model, then you might need a big machine with a lot of RAM. And if you later on can just scale this horizontally over your whole cloud, and you have a framework for this, like TensorFlow serving, then it might perfectly work. In case you don't have any kind of pre-processing, because you would expect your deep learning model to do the kind of feature engineering or whatever. But if you have some scikit-learn model, it might become much more complicated. So do you mean any kind of specific system?
Just in general.
Yeah, so in general, you have to again check what can you use. Can you use, for instance, the whole scikit-learn functionality or TensorFlow, or are you restricted to something? And again, also how are you going to access the data and how much data is? So it's again depending heavily on your use case. Thanks. Okay, thanks for your attention, and yeah.